some naturally associated structure. Things, no problem. And and I will describe something that is not often discussed, which is what we call the associated bundle of region. Then we will try to see how we can realize basic form and what we call dressed integral through the dressing field method, and then show you how it generically applied in that context, how it allowed to reformulate general relativistic theories in a completely invariant and relational way. So here it goes. So the field space will be the set of fields, right? So essentially from some manifold to some vector space, some space, vector affine space, right? Collection of fields, and M will represent space M. Again, quotes, representing quotes for the reason we just saw. So the group, the diffeomorphism group of M acts on the space of fields on the right via pullback, right? So if I take a pair with a field and a diffeo, I compose the pullback like this. So that's a right action, hence the R here. And I will denote it like this with a tiny index phi to denote the diffeo transform field here. So this makes again, if this action is nice, free and transitive and everything, if you remove all killing groups of fields and whatever, as is realistic, right? In realistic situation, you don't have any killing symmetries for any field configuration. That will make the field space into a principal bundle, right? Meaning that given a point in the field space, you move with the diffeomorphism group, you move along, and you generate the diffeo orbit of the fields. So those are the fibers in the field space. And there is a canonical projection onto the moduli space, which describe essentially the physical degrees of freedom, right? All that is, yeah. Yeah. So the ME, again, in the nice case in which this can indeed be described as a principal bundle, this would be an infinite dimensional manifold, and each point represents a gauge orbit. Like, for example, if you have a metric here, like let's say Schwarzschild, and you act with diffeo of the manifold, you can generate diffeo transformation of Schwarzschild. But they are all the same solution physically. And so what's physical in that solution is described by a point here. Okay. Yeah. Yeah, the field space, yes. Yeah, you will assume that they are smooth, for example. They are different. Generally, they will be differential forms. So this is a zero form, for example. So a function. So a smooth function, infinitely differentiable. A nice classical field. No. That's the point. It's a kinematical space. There is no yet functional constraint, field equation, gauge fixing condition, nothing. It's just like, for example, it can be, I don't know, you set a spin-off fields, whatever they are, or the space of gauge potential, Young-Mills, whatever they are. Yeah, completely, yeah. Just smoothness, say. Then you have, of course, the Lie algebra of the diffeomorphism group, which is nothing but the vector fields on the base manifold that will generate, as we know, a tiny vector tangent to the fibers, right? So a vector field. So this X is a vector field on the manifold M, the finite dimensional manifold that represents space-time. But this will generate a tiny motion into the gauge orbit, right? Which is just which is tangent to the orbit, therefore. And that's the infinitesimal gauge transformation of the field configuration phi. So the diffeomorphism group is what is called a structure group of the field space. In some aspect, in some quarter of the literature, this is what people call the field-independent gauge transformation, or field-independent diffeomorphism, right? Now, we have, since this is now, we see this as a bundle, it has natural transformation group, the first of which is, as Lucas was presenting you this morning, the group of automorphisms. So the peculiarity of group of automorphism is that it preserves the fibration, because as a manifold, this guy has a group of diffeomorphism of his own, but a diffeomorphism could take 2 points of the same fiber, send 1 point to one fiber, another point to a next fiber. So it will destroy the fibration structure. The automorphism, thanks to this condition, ensure that I map fibers to fibers, which mean in particular that those guys, they induce, so they move fibers to fibers, and they will therefore induce diffeomorphism of the moduli space. So if you project, so to speak, this group, it will move a solution to another solution. So it's really a physical transformation between different solutions when you look at them on the base space. So there is a subgroup of automorphism, which is a vertical automorphism. So those are that preserve the vibration, but in a kind of a trivial way, because they induce the identity transformation of the moduli space, meaning they move only vertically, hence the name. And it is isomorphic to the gauge group of that space. So what's the gauge group of that space? Well, it is made of functionals that takes a point here, so a field configuration, and spit out a diffeomorphism, right? And it has to transform like this, and the isomorphism is given by this, but it's a detail which is not important. Only point being that these guys, the gauge group of the field space, is what would be called the field-dependent gauge transformation, or field-dependent diffeomorphism in that case. Because the bold psi, it is a functional, it is a diffeo, for sure, but it is a functional of the field. So it's a field-dependent diffeomorphism. So the structure group, the normal diffeomorphism, the one that don't depend on the field, they constitute the structure group of the principal bundle field space. They are field independent. The gauge group are the field dependent one. Yeah, no, it's still the small m, because it's so the curly m indeed is the moduli space. It is an infinite dimensional space. Tiny m is the finite dimensional space, aka space-time, representing space-time. But so this point is that this guy here is bold compared to that one that is not, just because it is field dependent. Yeah, it's barely see. I'm sorry, it doesn't show very much, but yeah, it's bold. So that guy is not bold. That guy is bold. That psi here is not bold. That one is bold. Hopefully the difference. This one is not. Those two. That one is, for example. So it doesn't show, but okay. But anyway, it's a technicality, it doesn't matter. The key point is the conceptual difference between the structure group, field-independent diffeos, and the gauge group, which is the field-dependent one, which induce vertical automorphism of the bundle. So again, we have a short exact sequence, but again, that's a technicality. It doesn't, it's not very important. So I move on. So as a manifold, the field space has a de Rham complex, meaning that it has a space of forms, and a de Rham derivative, which I will write as a delta, like the variational derivative, right? When we do variational problem. So this delta is the analog of the D, the de Rham derivative in infinite dimensional space, right? The partial d mu of the. And so a variational form I will write as the formal external product of delta phi. Delta phi is a field variation, right? So it's a basis one form. So the delta phi is the analog of the dx mu in finite dimensional geometry, dx mu, and it is a functional of the field space. So let's see. So both the structure group and the gauge group act on forms, typically by push forward. So let me move on, because those are details that maybe are not super important. So the point is that the action of the structure group define the equivariance. The action of the gauge group define, of course, gauge transformation, quite naturally, like that. And the only reason why I spot these transformation rule, because it acts, those two groups, structure group, gauge group, they act on form by pullback, but therefore on vector fields by push forward, right? From standard differential geometry, it acts by push forward, and the result of the push forward by a vertical automorphism is this, which tells you two things: that the gauge transformation of a form on the field space is controlled by, first, its equivariance through that piece, and second, its verticality property, meaning what is the result of evaluating a form on the vertical vector field. Because you have a piece here which is a tiny vertical vector field here. Okay, again, technical detail, but I will show how is it relevant for later. Next, we have remarkable space of forms. I will not go over this too long, because Lucas already showed you before example of that. So if you have a representation of diffeo, the equivalent form are those that transform, whose equivariance, so result of this operation, is simple and just controlled by the representation of the diffeo. So for example, for the basis one form delta, again, the infinite dimensional analog of dx mu. The equivalence is given simply by the pullback representation, if you like. And by definition, it's verticality property, meaning what it means when I evaluate these field variation along a vertical vector field is that it gives me the infinitesimal transformation of the field, meaning this Lie derivative along the vector fields. And so given those two properties only, so equivariance, verticality, I can read off immediately that the gauge transformation, so the field-dependent diffeomorphism transformation of delta phi will be this. So it's a one-line on by-side computation that is much longer to derive via heuristic computation, as it is done often in covariance phase space literature, for example. Then again, you have, as we discussed earlier this morning, a generalization of that situation. So we generalize representation by ecocycle on the group of diffeomorphism. So G will be another group, unspecified, another group. And now the equivariance of the form is controlled by ecocycle like this, which satisfy this defining property. And again, you see why does it generalize representation, because if you forget about the first slot here, you see that C becomes just a group morphism of diffeo into G. And this rule enforce compatibility with the right action of the diffeo of the structure group on the field space. So infinitesimally, if you linearize this cocycle, you get a cocycle on the Lie algebra of diffeomorphism. And its transformation property, which is this, is the linearization of that one, and it is compatible with the action of the Lie derivative on field space. So for those who knows a bit about anomalies in quantum field theory, you may recognize that this is a generalization of the Wess-Zumino consistency condition for gauge anomalies. The consistency condition for anomalies doesn't have this piece here. The reason being that they are cocycle with value in an abelian group G. So if the group G is abelian, the bracket G is abelian, the bracket doesn't exist. So you have just this equals this, and this is exactly the Wess-Zumino consistency condition for gauge anomalies. So just to tell you that the cocyclic structure is the thing that control the gauge anomaly structure in gauge field theory. Yeah. A bit like last time, it will depend on which form exactly you are dealing with. So for example, in quantum field theory, alpha will be let's say a path integral, for example, in which case it is complex valued, and the G in question is just U1. Mm-hmm. So I'm not sure I follow, because in that case, what I'm describing here, for example, is the geometry of the field space, which is an infinite dimensional bundle, no? Okay. 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 Yes. Yeah. Not diffeo, you mean? Okay. Mm-hmm. Yeah. Well, yeah, in a sense, yes, because as we said, indeed, if for that guy, if you were to forget about this, so that first slot, that is just a group morphism in that case between diffeo and G. So it would be a kind of, yes, you're right, a representation of diffeo onto something, the something being, okay, any G space. So if you have a vector space V, for example, on which G acts as a group, you would have a representation of diffeo on that vector space, for example. Well, that's not necessarily what you, and that's for example, what you have here. So that's why I talk about the path integral, for example, because if you have alpha here being a path integral, what this stuff tells you is that the way the path integral transforms under diffeo is through an object like this, which is a U1 valued object. So it would be literally the Feynman path integral. So it would be an integral on the field space, which is complex valued, or even simpler than the path integral. Just take exponential of I h bar of the classical action. So the weight of the path integral, right? Just remove the problematic mathematical piece, which is the integral over the measure on field space, so remove that. Just keep the exponential I h bar of the classical action. If the action transform, like take again Chern-Simons 3D. So the action of Chern-Simons in 3D is not invariant in transform, right? For a not for diffeo. That's for suppose it is not diffeo here, but it is a gauge group, so SUN gauge group, for example. You would transform the action like that with a cocycle. If you exponentiate this, you have an object. I call it alpha, say, and you have exponential of the non-invariance piece. This guy is a cocycle, is a U1 valued cocycle like that, the same. So it will be, so it will be a representation, a field, if you like, to think of it like that. It's kind of a field-dependent representation of the gauge group. So, okay, diffeo here, suppose it is H, curly H, gauge group, SUN gauge group. So it would be a U1 valued field-dependent representation of a gauge with a gauge parameter, SUN gauge parameter, acting on an object here. With the absolutely, because absolutely, yes, because the point is that you have an object on field space, a Lagrangian, an action, path integral, the exponential of the classical action. The question is, how does it transform? It will transform in some way. The claim is the most general way it can transform is through a cocycle like this. And so the G, of course, the G in question would be, typically in most cases, it would be U1. No, in many, I mean, not most cases, but in many important cases, it will be just U1, that stuff. But maybe we should see an example of that after. So let me go fast forward. Tensorial form, so the horizontal form, vanishing on vertical vector fields. Tensorial form, they are nice because they have a nice transformation. The tensorial form, hence the name, right? Why they are called tensorial? Because they are homogeneous transformation, aka tensorial transformation, under the symmetry in question. So for the normal tensorial controlled by the representation or the cocycle. So this may let me pass on this, maybe fast. Just to enforce what I just said, that essentially those cocycles, in that context, they're exactly the geometric underpinning of the phenomenon of anomaly in gauge field theories, or general relativistic gauge field theories. So, okay, for this to see very fast, standard stuff, the delta, the de Rham derivative, it does not preserve the space of tensorial form. Okay, it's classical stuff. That's why you need to introduce a connection to get a covariant derivative on that space, right? So typically a principal connection on the field space I just described would be an object, a one form on the field space with value in the Lie algebra of the diffeomorphism that satisfy those two properties. So it has an equivariance and a verticality property. Those are typical of an Ereshman connection, just applied to the context in which the structure group is the diffeomorphism group, which implies that the gauge transformation, the field-dependent gauge transformation are those, right? That resemble the one you would find in gauge in SUN theories. No, you have like a gauge parameter -1 connection, gauge parameter plus gauge parameter but -1 d gauge parameter. That's the kind of inhomogeneous transformation that are typical of a connection. And you have therefore the covariant derivative on tensorial form defined like this through an Ereshman connection. And the same go with the curvature defined as usual, satisfying a Bianchi identity. And just to spot that it is the same for a twisted connection, to preserve the cocyclic tensorial form. Just the equivalence is a bit more complicated. It is inhomogeneous, but the gauge transformation is essentially still the same. Important subspace to notice now, I come to the point of the thing, is the notion of basic form. Why are they interesting? The basic form on the principal boundary general, in the field space in particular, is that they are trivially gauge invariant, right? They are invariant under field-dependent gauge transformation, and the delta, the de Rham derivative, is a canonical covariant derivative on the space of basic form. right? So you don't need to introduce an extra structure, an extra connection, right, to get a well-defined differential operator on those forms. Which means that we have something called the basic subcomplex of the bundle. And the basic subcomplex is super interesting because it is isomorphic to the de Rham complex of the base manifold. And remember, in that context, the base manifold, the moduli space here, is the one containing the degrees of freedom of the theory. Right? It is because M is the space of orbits, right? The space of physical degrees of freedom. So this would be the space that physically we are interested in. But it's for problem being that in typical fashion, those moduli space have no practical representation. No, I cannot manipulate easily the moduli space in general. But fortunately for us, there is an object that is well defined on the bundle, which is the basic subcomplex, which is exactly isomorphic. So what I want to do when I do physics is I want to be able to work in that basic subcomplex here. I want to be able to be there. So whenever I have an object on the field space, a Lagrangian, an action, a path integral, whatever, the field equation, typically they will transform non-trivially under the symmetry, gauge group, or diffeomorphism in this case, meaning they are not physical, not yet. So what I want to do is to be able to create, to construct a basic counterpart to that object that will live here, right? And the point is, and the question is, since this is what is physically interesting, is, again, given some form on the field space, can I build a basic counterpart? Well, that's exactly what the dressing field method is supposed to do, right? So we will see. But before coming to that, one word about something that is, I find quite neat, is the notion of associated bundle of region. So the idea, the classical idea of an associated bundle, when you have a principal bundle like this, is to say, if you have a representation of the structure group, you can build another vector bundle whose fibers are the representation space of the structure group. So in that case, we can consider the set of open set of region of the manifold M that represents space-time, and consider it as a right diffeomorphism space, meaning that there is a right action of diffeo on the space of open, which is simply like this: is that an open U is mapped to psi minus 1 U. So I just map an open space, I shift an open space through a diffeomorphism somewhere, right? This is a right action, that's why there is a minus 1 here. And so we would define the associated bundle of region as simply being the quotient of the product space, which take the field space and that space, by an equivalence relation, and the equivalence relation is that one. Is that if I have fields defined on an open set, they will declare to be equivalent to the pulled back field on the shifted back region. And this pairing is diffeoinvariant by construction. No? So this construction encodes space-time as understood via the point coincidence argument, because it tells you essentially that the region, the point of space-time, are defined in a diffeoinvariant way through the field content. And in a sense, this is what you are acknowledging here, is that you say, I have to pair fields and region. I cannot consider region on their own, standing on their own as object. Neither can I consider fields on their own as object. I have to consider them as pairs, and only the pairs moving together make physical sense. So, how would you understand integration in such a context? You would say that integration is just a pairing between two objects, so a region, so an element in that space, and some form on field space that is also a form, a differential form on the region, so that I can simply integrate that form on the region, and I will denote it like this. And that pairing is by definition diffeoinvariant, right? The theory of integration is built so that it is diffeoinvariant. No? So meaning that the integration pairing is well defined on the bundle of region. It's an operation well defined on that bundle here, the bundle of region. So the action of the gauge group of that space on integrals is simply defined in that way. I will act on a pair by gauge transforming the form on the field space and by shifting the region, inverse shifting the region by a field-dependent diffeomorphism. And therefore, the gauge group acts on integral in that way. Right? That would be the action given an integral. This is how I act with diffeomorphism, field-dependent diffeomorphism on an integral. Now, why did I say all of that? Yeah. And in particular, of course, if you have a tensorial form, the result of which here is just to have in front of alpha psi star pullback, then by construction, because of this, the integral will be invariant. But notice that it means that integrals, despite being by construction invariant under the action of diffeomorphism for integrand transforming that way, it doesn't mean that they are always automatically gauge invariant under field-dependent diffeomorphism. It is true only if the integrand alpha is a tensorial object here. So, for example, the action is built that way to be automatically diff invariant. So the dressing field, now I go about it. So the point of the dressing field approach, in one word, is to, in some sense, give a realization of the bundle projection and define basic version of a form alpha by pulling it back. So it will also allow us to define dress integral and give an integration on space-time. So let's see how it works. So in that context, what I will call a dressing field is a map from the field space into the smooth map between a model manifold, which and my manifold, the one supposed to represent space-time, which by definition should transform that way. So it looks like the one Lucas has been presenting this morning. It means that the U as a functional of the field, when it has to transform under diffeomorphism in just this simple way here. So it means, well, okay, this we have already said, but okay, it means that a dressing field is not an element of the gauge group in general, right? It transforms like that way, so that was the equivariance, that is gauge transformation, therefore. And it allows, if you have such an object, it allows to define a surjective map from the field space onto the moduli space, explicitly given by the following formula. So I will take my field, and I will map it to phi u, which is just the pullback of phi through that map u that is here. These we call the dressed variables, and they are by construction diffem invariant, meaning they commute with the right action, or rather they annihilate the right action of the bundle, right? So this is what it means. So it means that it collapses all the gauge orbit into a single point. So that's why you realize the dressed object is essentially the same thing, or a coordinatization, if you like, of a point of the moduli space, which represent the physical degrees of freedom. So in a sense, this dressing map here, this object, is essentially the same thing as the projection of the field space. Now, what's the idea behind the dressing field approach, very broadly, is to say, suppose again you have a form on your field space, so it depends on the variation of the fields and on the field itself, and it transformed in a non-trivial way under diffeomorphism. Suppose you will take the counterpart of that guy on the moduli space, meaning that you take the same functional expression alpha, but you imagine that he would act on the base delta of the moduli space, and depending only functionally in the same way on the orbit class. And formally you say, well, I will define the dressed form as simply the pullback of that guy that lives on M back into the bundle. So if you are on the base manifold and you have the projection or the map that goes from the field space down to the projection, if you have a form at the base space and you pull it back, you move back onto the field space. No, that's the concept of doing this operation. But the nice stuff is that by definition, this guy is now basic, because the definition of basic form is that they are pi star of a form on the moduli space, right? So that's what we got here. So this we know how to do. For example, it was defined here, no problem. The only question is what is this, and a bit of computation tells you how to do it, and that's how you get the rule of thumb that Lucas has been talking about. Is that to know exactly, this is very formal, this is conceptual in a sense. Now, concretely, how do you do it? You use the fact that a vertical automorphism and the dressing map look exactly the same. It's again a kind of pullback. So what you do is simply you compute the gauge transformation of your object, and you get something, whatever, that depends on your object and the gauge parameter. And then you just substitute your gauge parameter by the dressing field. And that will give you the functional expression of the dress guy. So if you want to know what's the dressing of, if you have an alpha, you want to know what is this dressing that will be invariant, you say, let me gauge transform alpha. I obtain something, I replace the gauge parameter by the dressing, the expression that I got automatically will be gauge invariant. So for example, let's take again the example of the basis one form that you have here. We've said its equivalence was this, its verticality was this, so that we had that this gauge transformation was given by this expression under the diffeo, the gauge dependent, the field dependent diffeo. So what would be the dressing of that guy? Well, I write it like this, and I simply, in that expression, replace psi by u, and I got this. This expression seems a bit barbaric, but if you were to transform phi again and u under diffeomorphism, you would check that this expression is fully invariant. So that guy is the basis of basic one form. So you can replace, so just to tell you that, okay, you know, we got that one, you can plug it here, and now you have a completely systematic way to say how, given a form whose functional expression in terms of delta phi and phi I know, how do I get the dress counterpart? I know, I just take the same functional expression, and in its gauge transformation, I just replace the psi by the u's. So that way of doing things has a kind of nice relational interpretation, because the dressing field is, by construction, right, it is dependent on the field space, meaning to build my dressing field, my U, I use the degrees of freedom that I have available, that are there. So it means that the dress field is naturally understood as representing the invariant relation among the degrees of freedom that you have, right? Because what I have done is coordinatizing some of the degrees of freedom of phi with other degrees of freedom of phi that I knew in the dressing field. So this is the relational coordinatization. So it formally implements the notion of invariantly codefined physical degrees of freedom in a formal way. Okay. So we have seen how to dress forms. Now we can very naturally see how you can dress integrals. We've seen how integrals transform under the diffeo group of the field space. So we will apply the rule of thumb exactly the same. So if you have so first, okay, so if you have a pair like that, the dressing would be something like this. And so integrals, so we have a bare integral, so to speak, of a bare integrant under a bare subspace, subregion of the manifold. The dress integral would be defined like this. So again, it would look, if you were to gauge transform with diffeomorphism that guy, you would have tiny psi here, psi here. So again, rule of thumb, I just replace the psi by a u. And what I got here is a dressed integral in which both the integrant is diffeo invariant, but also the region now, this object here, is which we call a dressed region, this guy is also diffeo invariant, right? So it was again completely just the rule of thumb that we've just illustrated here to get a dress integral. And okay, so let's remark. So about space-time. So this guy, this dress region that we have here, they are diffeo invariant by definition of how diffeo act on you and on the dressing field, right? We get this. So we have defined diffeo invariant region, which are, and they are defined in a field-dependent way, because again, remember that there is field degrees of freedom into U, into the dressing field. So those are diffeo invariant field-dependent region again. So they are again the formal implementation of the point coincidence argument that tells you that you should define true physical spacetime region through the field content. So this is in a sense what we have here, what you call so those, all the set of all those regions are the subset of the dressed spacetime, which is the diffeo invariant physically meaningful spacetime here. And so it turns out that dressed integral, they represent integration of physical quantities over spacetime, right? So this does not, because this is not diffeo invariant, this is not diffeo invariant, so this integral represent an integration operation, but not over physical magnitude, physical quantity. It represents them in some way, but not directly. So this guy does the job, in a sense, more immediately, because both the integrand and the integration domain are diffeo-invariant in that case. So as an aside, notice that therefore the boundary of a spacetime region is automatically diffeo-invariant, of course. Which means that there is a claim that you often encounter in the literature, according to which you hear that boundary of spacetime break diffeo-invariance. This is, at best, this is misleading, because either it is wrong, because spacetime, of course, is physical, and therefore, as anything physical, it is insensitive to diffeomorphism-invariance, or you are simply saying, yeah, sure, the boundary of a region of M is not diffeo-invariant, but that is trivially true, but it's physically an empty statement. Yeah. Yeah. Yeah, 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 yeah. Yeah. Absolutely, yeah, yeah. Absolutely, yeah, that's it would be exactly right. Because in the end, so that dressing here, at the very minimum, what you would need, well, or maybe you have less, if you, like two, if you want to describe physically submanifold subspace. But for sure, for a full bulk region of space-time, you would need at least enough degrees of freedom to be able to create a dressing field that is 4 scalars at least. That will give you the natural quantization of space-time. Yeah, or you would say, okay, this applies, but only on submanifold in which your fields are defined. Suppose you have, field defined only for some reason, well, it would be distributional in a sense, a bit strange, but okay. Having field defined only on submanifold, you would be on that submanifold, still be able maybe to apply this unchanged and say, okay, on this, for example, if you want to describe, I don't know, um, typically, I don't know, if you want to describe horizons or stuff like that in a truly physical way, you would say, okay, I need to have degrees of freedom that I can use to coordinatize physically my horizon. Otherwise, I don't know what I'm doing. I think we will have maybe an example of that. So yeah, so this precise question has been discussed in that paper with Lucrezia a couple of months back. So let's apply this in the context of general relativistic theory. So what we have is a Lagrangian. So it's a functional, it's a zero form on field space because it doesn't contain any delta phi at first. So it's a zero form on field space, but it is a top form on some region U, so a bulk region, 4-dimensional region, for example. And the action is simply, as you know, the integral of the Lagrangian. The variational principle, well, is just applying D, the Durham derivative of field space, onto L, which gives me, therefore, a field equation and a boundary term. D theta, it doesn't show much, that is a theta, but it's a theta. It's called the symplectic potential, often in coherent phase space approach. And those are this is since L was a zero form, no delta, delta L is a one form, therefore, on field space, because it contains delta phi here in both cases. So hence it is a one form here. So those are the field equations. And this is a pre-symplectic potential, as I just said. The field equation one form is equivariant, meaning it transforms like this under diffeo, as you would expect from a general relativistic theories, meaning that the space of solutions is again a principal bundle with diffeo as a structure group, which is exactly the statement of GR, or general relativistic theories. You want your solution to be a bundle under the symmetry group. So that much you would expect from GR physics. But now there is more to be said, is that now you can look at the action of the group of field-dependent diffeomorphisms on that structure. It just so happened that if you want to look at the verticality property, because this is a one form, as I said, the field equation one form here, meaning that I could evaluate it on vector fields, for example, in particular on vertical vector fields, the one tangent to the fiber. And it just so happened that I get this. Again, you can trust me at my word, take me at my word. But so now that I have this and I have this, it means that I know how the field equation transform not under the structure group, because that's the structure group, so the field independent diffeo here. What I want to know is the gauge transformation, meaning how the field equation transform under field-dependent diffeo. And this is non-trivial, but it can be a read-off for those two, and it is simply this. So these are the field-dependent diffeomorphism transformation of the field equation of general relativistic theories. And it's nice because it tells you this, that you see that the space of solution is stable under the gauge group, right? which means that the covariance group of general relativistic theories is much bigger than you would imagine a priori. You would have imagined that it is just, so to speak, but the field independent diffeo, turns out it comprises also a priori all the field dependent diffeomorphisms, which is non-trivial. And I think the first to have noticed this, I don't know if it was written there. No, maybe after. Yeah, okay, so it is there. So I think it's Bergman and Comma were the first to get a hint of that when they were considering vacuum GR, and they were looking at metric-dependent diffeomorphism. They were using canonical analysis, I think Hamilton analysis, and they were seeing that it seems that the group of symmetry of GR, or vacuum GR, also includes metric-dependent diffeomorphism. So the framework here you see of field space systematize completely the result to any general relativistic gauge field theories. So this is the background, because this is not well, okay, we wrote that, but I mean people other could have. This fact though is absolutely key to the possibility of a relational reformulation through dressing, because again you remember, question now is, okay, I have this Lagrangian, this action, I have all those objects, none of them are invariant on the field space, so none of them are truly physical in a strict sense. I would want to have the basic counterpart of those guys. And I said through the dressing, I get a basic counterpart of something if once I have the gauge transformation, I just replace the gauge parameter by a dressing. So this is what we do now. Next, we say, okay, let's dress the Lagrangian, which is just a pullback of the naked Lagrangian. I can dress the dress action, which is the dress Lagrangian, which is just a functional of the dressed field on a physical region like this, which is a space-time integral. So L being tensile is the same as the bare action, meaning the same number. Numerically, it gives the same number. But now, one thing that notice that I didn't insist on that yet, but when I was writing notice one thing, when I was writing the variational principle here, in some subtle sense, I was doing something that is not legitimate geometrically, because L is an equivalent, even a tensorial zero form, but delta L is not, right? Because the problem is, as we say, the RAM derivative, delta in that case, doesn't preserve tensoriality. So when I write delta L, well, I can write it, of course, but the point is that the object here is not of the same nature as the original object. So in a sense, you could say that geometrically, it's as if the variational principle using the D on L is not truly well defined as a geometric operation. Now, once you have dressed everything, since you have obtained basic guys, as you remember maybe, we said that on basic form, the RAM derivative is a canonical covariant derivative, meaning that if alpha is basic, d alpha is basic also. So once I have the dress Lagrangian, like this, d of the dress Lagrangian is a legitimate operation, because LU is basic, delta LU is basic again. So this is now super well defined. This gives us the dress field equation and the dress symplectic potential. That's, well, by the way, the dress symplectic potential will give you what in the covariant phase space literature is called extended phase space through edge modes. The edge modes are a case of our dressing field, essentially, are ad hoc dressing field. Why ad hoc? Because they are not built from the field content. They are introduced by hand into the theory to make things invariant, so they can reverse Stuckelberg field in that case. Those are field dependent, or they should be field dependent dressing field in that case. But in particular for the field equation, the relational field equation is that one. And it is a basic object, meaning it is strictly invariant under diffeomorphism, meaning also that it has a perfectly well-defined Cauchy problem, for example. It doesn't suffer from the whole argument, that object. So the point is that the space of physical solution is coordinatized by or sorry, coordinatize the space of Bayer solutions. Yeah, so that's the relational field equation, like that. And yeah, something that maybe we should stress, interestingly, is that in a foundational conceptual sense, I would say that the invariant field equation are those that are confronted to observation, of course, because you can never compare the bare field equation, your undressed one or the non-invariant one, to experiment, because those again suffer from diffeomorphism covariance, therefore from the whole argument. So what happens is that typically what you have to do when you have the bare field equation is supplement them by other functional constraint, aka gauge fixing, to ensure that the combined system field equation plus gauge condition has a well-defined Cauchy problem. And this is what you compare to experiment in some way, with the gauge fixing, which typically is not chosen completely arbitrarily, but have to make sense given the physical situation. Well, given the physical situation means that actually you are choosing a gauge fixing which is actually aligned with degrees of freedom that are present in your theory, physical system, you know, I don't know, the LEGO, the arm of LEGO when you go gravitational physics, for example, that kind of stuff. So what you are actually doing is coordinatizing the gravitational degrees of freedom, for example, if you do gravitational waves, with another physical system, which is the Earth system, for example. So what you're actually doing is kind of addressing. You are essentially coordinatizing some degrees of freedom with other degrees of freedom. So those are the ones that, again, conceptually are confronted to experiment. Yeah, okay. So this way of doing things unifies and systematizes diverse approach, several constructions in the literature. So I list only a few here. For example, the notion of dynamical reference frame that has been developed in the past, I don't know, 5 years maybe. The notion of geodesic dressing, gravitational dressing, a la Giddings and others. As I said before, the notion of gravitational edge mode that has been introduced by Donnelly and Fredel in the context of extended coherence phase space. So this notion of edge mode, as I said, is what we would call ad hoc dressings because they are not built from the field available degrees of freedom that you have. They are introduced by hand into the theory. So in the case of GR, for example, to just pitch a super fast example. So you suppose that you have a metric and let's say you're in cosmology, for example, you have a scalar field, like a dust field, right, as you would do in cosmological model. So what you would take is, you take the dust field as being your dressing field in that case. So in that case, the manifold N that was the source space of the dressing field is just the level set of the dust field density, essentially. So the dressing field is like that. And so the invariant dressed relational metric is that one. It's simply the metric. In a sense, this is the metric written in the coordinate given by the dust field, which is completely natural as a thing to do when you do cosmology, no? And so you can have the dressed Einstein-Hilbert-Lagrangian and the relational Einstein equation, or dressed. So the special case of this, in that case, it is this. And this is the dressed Einstein equation with maybe something funny. Okay, well, this way of doing things, it's basically the notion of scalar quantization that is done by first by Kretschmann and Komma, I think. Oh, okay, different way of doing scalar quantization. I think Kretschmann and Komma did use not a dust field, that was Brown, Couchard, Rovelli, and DeWitt, but Kretschmann and Komma did use the metric, using curvature scalar, curvature invariant to give a kind of invariant quantization of the manifold. But in that case, okay, this is an example in which we reproduce, for example, the DeWitt, Brown, Couchard, Rovelli approach of doing things. With maybe one funny thing to notice here is that in that formulation, you see that the metric and matter degrees of freedom feature on both sides of the equation. In the bare equation, typically we say, the left-hand side is pure metric, nothing else. On the right-hand side, there is the physical, the matter degrees of freedom in the energy momentum tensor, and the metric degrees of freedom also to define the energy momentum tensor. But the left-hand side is supposed to be pure gravitational. In that dressed version, you have both degrees of freedom featured on both sides. Again, showing the kind of completely intricate relational structure that the invariant theory should have by definition. So to conclude, the dressing approach, as I've shown you, is just a way to build basic form on free space and to define dressed integral. Conceptually, it has a very natural relational interpretation, provided you build your dressing field via the available degrees of freedom, and you don't import them as extra degrees of freedom. And it gives you natural relational variables that implement the point coincidence argument. And thus it allows a kind of invariant relational reformulation of general relativistic theories. This extends very naturally and seamlessly to, as I say, the full framework of general relativistic gauge field theory. You can do the same game with adding a gauge, an internal gauge group. It will work pretty much the same. You just extend the field space. You extend the structure group of the field space to include an internal gauge group H like this. And it allows you to, again, build relational variables that are not only diffeo but also gauge invariant, and therefore to bypass the generalized all-in-point coincidence arguments. And these, we have described some of these in a paper with Philipp Berghofer from Graz. And so the broad framework allows a relational reformulation of GRGFTs in a completely systemic way, meaning that, as Lucia was saying at the beginning, this nice formulation is that this all stuff is a conditional proposition. It tells you, if you manage, here is addressing how it is defined. If you manage to build one, extract one, identify one in your theory, then here is the completely algorithmic way by which you can build the full relational invariant in theory. Of course, the difficulty becomes, in each given model, can I build the dressing? Can I extract the dressing field from the degrees of freedom that exist or not? Yeah. And so all of this framework has been described in that paper in 24. And now we are developing the next step. So the same logic applies to supersymmetric and supergravity theories. Some of this has been described in that context. It applies to quantum mechanics, as you saw a bit this morning. Why? Because we first gave a kind of geometric, bundle geometric formulation of classical and quantum mechanics so that we can apply the dressing in that context. That was the pitch. And it leads naturally, that framework, therefore, to the notion of what we might call relational quantization, which is simply, once you have a relational variable, you just quantize not the Bayer variable, but the relational one. And this is, for example, you can have a dress path integral, which would be like this, which is the path integral of the addressed fields. If it happened that the Bayer path integral, so without the dressing, had an anomaly, a gauge anomaly or a diffeo anomaly, these objects cancel it immediately, automatically. That has an inbuilt anomaly cancellation mechanism that reproduce and extends all these Vesumino counter terms that are often created heuristically and case by case, precisely to compensate and kill anomalies. So this flows automatically from such an object. And this is the kind of stuff that we are now developing with Lucrezia, especially that one, with invariant quantization and what we call an anomaly seesaw mechanism. And as a special case of this, by the way, funny thing, if you apply this in 1D, you get mechanics, for example. Particle mechanics is a one-dimensional field theory, right? In which you have a clock field, T of tau, and spatial field, X of tau. You get exactly a kind of general relativistic theory for the tau parameter, which is the analog of the M manifold of before. And in that case, the dressing in such a context would be the clock field. The clock field is a dressing field for the reparametrization symmetry of the T tau, X tau formulation of mechanics. And the dressed version, therefore, is just textbooks mechanic, therefore, in which the dress field phi u is just x of t. So the bare field phi would be x of tau, t of tau, and the dressed field is x of t. So in a sense, so it's a way to kill diffeo reparameter invariance. So this gives the motivational clue to develop this in a more systematic way to higher dimensional theories. And that's it. Thank you very much for your attention.
Thank you. That was great.
Thank you.
Questions?
How about quantum field theory? Do you think it could be applied somehow?
That's a super good question, and indeed, that's also a discussion we had with earlier today, and that's exactly what we are in now. As I just said just before, the idea is that so the the most naive way to do it is to say we have the classical theory under control. So we have this framework here for those in that paper with inverse reformulation for this symmetry. And so you would say, of course, typically what we do QFT. If you want to do QFT through path integration, for example, whatever way, typically you write a path integral on the bare field. So you see the path integral as a functional integration on the field space of before. But then you have to take care of many things. You have to take care, first you have to gauge fix to make the thing well defined. You have to maybe remove anomalies if there are any, and if you can, that kind of stuff. And so you have many complications. The natural thing to do with this formulation is to say, well, if I can dress, or again, conditional, suppose I have a dressing and I can do this relational reformulation, I want to quantize, again, very naively through path integration. So I will write such an object, and therefore I will try to develop to see what I get from those. So I will write, I don't know, path integral for that guy, correlator for, not for bare field, but for dressed field. I will introduce source, invariant source for that guy to, I don't know, maybe having the quantum variational principle, for example, try to find the Dyson-Schwinger equation that is dressed and blah, 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 to see how it goes. And that essentially you just apply the whole machinery that you're familiar with, not to the bare field, but to the dressed field. And the advantage of that is that first, doing this, for example, you don't have to gauge fix, first thing, because you have no symmetry. So this guy is not divergent. You don't need to gauge fix, meaning you don't have to, in the field space, select a slice with one representative by orbit on which you would restrict all the object that you have. So the Lagrangian, the action, and the path integration also. So you don't need to gauge fix. In particular, you don't need BRST gauge fixing either, for example. Because as a matter of fact, again, something we are writing in that paper as of now, just this week, you can show that in the same way that you have dressed fields, you also have you have dressed, or rather, you have dressed field. So sorry, let me back. In the BRST formalism, you have bare fields satisfying a BRST algebra, which essentially reproduce the infinitesimal gauge transformation of symmetry transformation of your field. The dressed field, they satisfy a dressed BRST algebra, which involve dressed ghost. And you can see that, you can prove that when you have a dressing field as the one you proposed here, the dress ghost becomes zero. It just vanish, meaning that you trivialize entirely the BRST operation, and therefore you have an empty BRST cohomology on the dressed object, which is natural because, as we said, the dressed object, they are basic by definition, so they support no gauge transformation. So you have completely factor out the BRST cohomology. So on dressed field, so suppose this define a QFT, for example. Suppose that you accept that path integral is okay, vaguely okay to do, at least, okay, not for national purpose, it's not, but at least for practical computational purpose, this is the way to go for Lagrangian QFT, for example, the path integral. So suppose you are modest in your ambition, as we are for now, you just say, okay, let me use path integration, at least that guy is not infinite, it is finite, and it bypass gauge fixing, which is not bad as a starting point, and then you can try to apply the machinery. For more for national purpose, meaning really going into serious stuff like algebraic or axiomatic QFT, that kind of stuff, as of now, I have no idea how this kind of structure export to that context, mainly because, as I said, the whole approach of the dressing notion is to start from a bundle geometric approach. So unless I know what would be the map between the field space and the key notion of the field space, Lagrangian actions, path integral, and a more algebraic starting point for QFT, I wouldn't know how to map this dressing approach to a algebraic context. But if such a dictionary is given, I guess it becomes manageable to try to say, okay, how can I have this kind of relational structure? I guess, I mean, my very low-level intuition on that front would be that in QFT you want, I don't know, algebra of observable or something, and symmetries would be automorphism of those algebra, something like that. And so the idea is that the dressing is the thing that kills the automorphism, in a sense. Okay, so the question would be, if you have what we would call a bare algebra of in your arithmetic or algebraic QFT, if you have a bare algebra of whatever operator or something, you still have somehow, I guess, automorphism of some symmetry, so of local symmetry, diffeo of gauge, acting on that algebra, I suspect. And so the point would be to say the analog of the dressing would be what systematic operation should I do on this algebra so that I factor out the automorphism of the algebra, essentially. But beyond that, I have no idea.
I see. So one idea I just had was, because the space of fields, they're just functions with values in the vector space. So if you naively, again, try to think about quantum fields, they could just have values in your operator algebra or something like that. And I guess everything is already like infinite dimensional and terribly complicated and kind of works.
Yes.
So maybe this.
Yes, you're right. It's true that the one intuition that maybe we can use is to say, but again, I don't know. It really depends. What's your favorite approach to QFT? Again, if you go by Lagrangian QFT, or if you go maybe I don't know. Again, algebraic or axiomatic or whatever. But it's true that one option is to say, okay, classical fields, they are smooth function or whatever. QFT, sometimes you hear say that they are, I don't know, operator value distributions, or at least distributions, something. So you could say, yeah, sure, so maybe let's see, try to extend the space of fields to distribution first, or the generalization of distribution, which are the RAM currents. It's a differential form generalization of distribution. So let's take the RAM currents, extend the space of fields. The space of fields are forms in that language, smooth forms. So you can say, okay, let's extend these to the RAM currents and maybe to operator or algebra valued the RAM currents maybe and see what you get. So yeah,
all you need is just the action of diffeomorphisms on whatever your fields are.
Yes.
I think you have this on distributions.
Yes, sure, on distribution for sure. That's the easy part indeed. But again, I would imagine it depends on which school of QFT you are. You know, what is the one you prefer? So yeah. So yeah, you're right. There are paths that are more easily manageable or flow more directly from that, and other that are more, well, again, you need a dictionary for me at least, because I don't know enough.
Well, especially if you want to stay as rigorous as you already are, then you don't want to go through path integral.
Yeah, absolutely. Yeah, sure. That's true.
Thanks.
Yeah. Thanks.
Quick question. So since you mentioned the path integral here, so now you integrate over the dressed field space, or like phi mu rather than phi. Probably this doesn't make it easier or more difficult to make.
Change nothing of the mathematical problem of things.
Okay,
just for whatever that means, you have a measure on dressed fields.
Okay.
Yeah.
But you said it can be sometimes finite, some hand wavy, when the other version would be infinite.
Yeah, right? Exactly. At least in a semi-hand wavy way, you can say, okay, in the bare field for sure that stuff integrates over the whole orbit. So you have all the volume of the structure group, the symmetry group. With that guy, in principle, no. It's analog of having integration, which what gauge fixing give you. Well, if you can think of it like that, is that when you have the field space, again, a gauge fixing will be a slice like this. So it gives you kind of a local section, so a map from the base space in which you know the degrees of freedom are into the field space like this. And so when you gauge fix, what do? You restrict a function on that slice. Geometrically, it's the same as saying I'm pulling back the object on the base space. So in a sense, the gauge fix action is integration on morally is the integration on the which is of course natural, because again you want to integrate over physical degrees of freedom. But if you have basic object, you can integrate in principle directly, quote unquote, on the field space, and it's the same, again, morally the same operation. So, but you will get something finite because you have factored out the action of the gauge group. So.
Okay, great. Thanks very much.
Thanks.
So yeah, maybe any other questions can be done the next. So you're here today and tomorrow as well. So yeah. So let's thank Jordan again.
Yeah.
Nice
Thank
talk.
you very much.